Hello, I'm Cillian from King's, and I will be discussing our work in cavity-enhanced photodetection. As we know, hot carrier Plasmonics offers many opportunities across a wide range of technologies. In particular, sub-bandgap photodetection afforded by Plasmonic Schottky devices enables integrated detectors operating beyond the bandgap limit. Here, we demonstrate a cavity-based platform for both enhancing the sub-bandgap current and also providing a means for dynamic reconfiguration of the operating wavelength. The proposed geometry is shown in Figure A. An optical cavity is formed between two gold films, which permits the resonant generation of surface plasmon pleurodons, SPPs, via resonance scattering from a grating incorporated into one of the mirrors. These SPPs subsequently decay, producing hard carriers that give rise to a photocurrent. Thus, by actively controlling the resonant conditions, we can directly modify the wavelength of resonant plasmon generation, and hence, by extension, the peak photodetection wavelength. Initially, the photocurrent was mapped from an isolated grating, i.e. without a cavity, in order to confirm the plasmonic origin of response. The output from an uncoated cleave fiber was scanned across the grating, with the resulting current recorded for each position. A clear hotspot with dimensions close to the milled grating is evident in the current map with the cross-section shown in Figure B. Once SPP-induced photocurrent was demonstrated, the second mirror, formed from the cleave fiber coated in a 10 nm thin gold film, was put in place and scanned in the Z direction in order to elucidate the influence of optical cavity modes. The spectral response of the cavity-based photodetector is shown in Figure A. The cavity modes are clearly apparent, providing much greater photocurrent than in the case of off-resonance, due to resonance scattering from the grating. This scheme also enables direct control over the detection wavelength, as the resonance conditions can be dynamically tuned. This is highlighted in Figure A, as the peak response is mechanically tuned over the spectral range of the laser by altering the Z position of the top mirror. The photocurrent from this resonance system is roughly 5 times greater compared to the off-resonance condition. The underlying mechanism of this resonant enhancement is further clarified via simulations presented here. When the cavity is on resonance, a clear enhancement is observed in the intensity of substrate SPPs. This leads to metal absorption at the substrate interface that is about 10 times greater than in the non-resonant case. The enhancement is further clarified by Figure C, which shows the electric field along a line in the Z direction as the upper mirrors move through the resonance conditions. In summary, we have successfully performed a proof of principle experiment illustrating the cavity-enhanced and wavelength-tunable photocurrent provided by a cavity-based architecture. The device exploits cavity-driven plasmonic modes to greatly improve the performance of sub-bandgap photodetectors. A 5-fold increase in the photocurrent was recorded compared to the non-resonant case, illustrating the potential of this approach, which can be adapted to include other plasmonic structures. We have also demonstrated dynamic reconfiguration with respect to the operating wavelength, thereby expanding the functionality and paving the way for future tunable photodetectors. Thanks for your attention. Cheers.